speaker is Jake Thomas, who's a third-year maths PhD student, learning all about possibility theory and active learning. So thank you very much for the talk that you're going to give.
Thanks, Jack, and thanks for inviting me to speak. So active learning is a super well-known area of machine learning, but it's one that's very valuable in certain situations. So I've titled this active learning because that's really the objective of what active learning is. The goal is to minimize the number of labels you need to learn with the machine learning model. So I'm going to talk about the approach we've taken to this using possibilistic Gaussian processes. So a quick summary of what active learning is. Essentially, we start off with a big set of unlabelled data points, and the agent has to choose a point at each time, which goes to some expert, which is the brain in the middle, which provides a label. And that's put into the labeled data set, and then the agent can learn from the labeled examples. So this is useful if finding labels is really expensive. So you might need an expert to label, or you need to run an expensive simulation, that kind of thing. So the rest of the slide, rest of the talk is going to be split into two parts. The first is types of uncertainty and possibility theory. And then I'll talk about the Gaussian processes and active learning. So starting off with the types of uncertainty. So if you've heard me speak before, you've probably heard me say something similar to this. This is a part of the talk where I convince you possibility theory is a good idea. So feel free to stop listening if you've heard this before. So there's two types of uncertainty, really. There's random, which is the one we all know and love. Rolling a dice, flipping a coin, that's random uncertainty. It appears when you can't predict the outcome of an event. And then the second type of uncertainty is deterministic uncertainty. So that's uncertainty about fixed quantities that aren't inherently random. So how many rabbits do I have in my magic hat? You could all make a guess, but you still have deterministic uncertainty about what the true value is. And the key difference between random and deterministic uncertainty is that by providing you with more information, I can resolve your deterministic uncertainty, which you can never do with random uncertainty. So say I show you that there's at least one rabbit in the hat, then I've resolved some of your uncertainty, and then if I show you there's actually 3 rabbits in the hat, then I've resolved all your uncertainty. So as a quick summary, random uncertainty can't be predicted even with perfect information, whereas deterministic uncertainty can be resolved with additional information. With random, when we're trying to describe random uncertainty, we're modeling the distribution of outcomes, and with deterministic uncertainty, we're modeling our information levels about a fixed quantity. So, and because of that, random can be modeled with probabilities, but deterministic uncertainty is not usually modeled particularly well with probability theory. So, and to quickly link that back to the active learning. So in active learning, the labels themselves might be an example of random uncertainty because they are something that you could potentially have incorrect labels, and that's random. Whereas the model parameters, so the true underlying classifier, for example, is deterministic, but you don't know it yet. Okay, so I'm going to try and very quickly build up a way of modeling deterministic uncertainty. So I'm going to use this example, and we're trying to model the uncertainty on the mean of a normal distribution where we know the variance is 1. So we want to try and model our uncertainty over mu as information, and that means we want to measure how consistent a particular value of mu is with our current information. So if we want to measure something, we're going to need to scale. So we'll just use 0, 1 to align with probabilities. And 0 will mean that a value is entirely inconsistent with our information. So say I tell you that the mean is positive, then every value less than 0 should have credibility 0. And if a value is entirely consistent with our information, then it should have credibility 1. Okay, so to build up a little bit of intuition, we'll consider 2 different cases. So if you have no information, according to our rules, every value is entirely consistent with our information because we have none. So everywhere gets assigned credibility 1. In the case where we have perfect information, so say I tell you that the mean's 0, then 0 is entirely consistent with our information, but every other value is inconsistent with our information, so it gets credibility 0. So the function will look like that. Okay, keep building up some intuition. So say I now sample our normal distribution 5 times, I get those 5 red dots as a result. Our credibilities are going to look like 1 at the mean of all the samples, because that's entirely consistent with the information we have, and then decreasing credibility away from the mean. And then as we get more samples, we're still normalized to 1 because the mean is still entirely consistent with our information, but it's now a narrower peak because those values further away from the mean are less credible. So the credibility of sets. We've got another example here. So there's 3 potential values for the mean, A, B, and C. A has credibility 0.3, C has credibility 1, and B has credibility 0.6. So I want to ask, what is the credibility of AC? So we're asking how consistent is the event A or C with our information. Remember, we're talking about one fixed value, so it can't be A and C in different runs of the experiment, like if it was random. It's either A or it's C. So the credibility of AC is how consistent A or C is with our information. And since C is entirely consistent with our information, the credibility of A or C is also entirely consistent with our information. Similarly, if we consider AB, B is 0.6 consistent with our information, so AB is 0.6 consistent with our information. And in general, the credibility of a set is the supremum of the credibilities of all the elements of that set. Any questions about that? That's the main difference from probability theory. Yeah, I'll take that as a very good explanation from me. Okay, so all of that is building into what possibility theory actually is. This is the rules of a possibility measure. So it looks a lot like probability measure. The only difference is that additivity is relaxed to sigma subadditivity. So we end up with an outer measure rather than normal probability measure. We can define possibility functions in a similar way to PDFs. But this time it's the supremum rather than the sum or integral that we'd usually get. Okay. I'm going to tell you a bit more of all like the theory, but I don't want to get stuck in the weeds, so I'm just going to tell you these things exist, and then you'll trust me, and we'll keep going. So we have uncertain variables, which are just the analogs of random variables. We have a Bayes rule that for working with both random and uncertain variables. So we can work with both random and deterministic uncertainty simultaneously. And you notice in the bottom there's a supremum rather than usual integral or sum. That is quite handy sometimes. It gives you some computational benefits, because usually supremums are much easier to calculate than integrals are. Okay. There's also analogs of expectation. So there are 2 notions of expectation in possibility theory. So the first one, E star, is essentially the mode, so the value that's most consistent with our current information. And then there's E bar, or the maximum expected value, which essentially returns to you the maximum, no, a reasonable maximum expected value. So it balances your the credibilities with the function value itself. Similarly, we have variance. This looks a lot different from the probabilistic case. This is related to the Fisher information, if anyone has worked with that before. But the key difference here is that this is a local property. In probability theory, variance tells you something about the whole function. But here it only tells you about something at the mode. Similarly, we've got the variance, which we define in terms of the precision matrix. And this is something I've worked on a lot, kind of developed most of the theory for this because it didn't exist, and it's quite important for the Gaussian processes. Okay, so as a quick summary, possibility theory gives you an accurate representation of deterministic uncertainty. You can do full Bayesian statistics with it. It's easy to combine with probability theory. There's easier computations in certain circumstances. It's got solid theoretical foundations. You have to trust me. And there's some structural differences like the expectations and the variances, which give you new perspectives on some problems. That was the possibility theory. Everyone okay? Questions? You're all trusting me. Perfect. Okay. So I'll talk about the Gaussian processes and active learning. So to start with the Gaussian processes, this is the Gaussian possibility function. It looks exactly like the probabilistic case. It's just normalized to 1 rather than to have integral 1. And a possibilistic Gaussian process is this function m and a function k. So m is a mean function. So say we're trying to estimate a function g, m tells you our mean estimate at any particular point for that function, and the k is the covariance, and it tells you how the function, how connected 2 points of the function are to each other. So if that makes sense in the picture. So here we have the function in red, which is a true function, which we're trying to model. And we've sampled that at 7 points, which are the red dots. Our Gaussian process is the blue line, which is the mean function, m, and then the shaded blue area is our uncertainty. So if we pick a particular point here, it's got mean 0, so our mean estimate for f at that point is 0, and it has variance 25. The blue shaded areas twice the standard deviation. That's why it doesn't line up with 25. So that was regression. We pick a latent function f, which is passed through some sigmoid function to calculate label probabilities. So normally we're just using the standard normal CDF. So here, like the probability of obtaining label 1 given the latent function is, oh, that should be f and f, not f and g. Yeah. So the probability of obtaining label 1 given f is the CDF, the normal CDF of f. And the probability of obtaining label -1 is just 1 minus the CDF at that point. So another picture to help. So these are our labeled points that we have already. So they've either got label 1 or label -1. That's the true latent function, which we're trying to find. We calculate the labels of the data points by passing through this latent function through that CDF. This is our Gaussian process estimate after we've fed at these points, and then there's our uncertainty. So you notice this time our latent function doesn't pass through the points because they're just the labels. They're not actually estimates for the latent function. And the other thing is that here we have, we still have uncertainty at the points that we've sampled because the labels themselves are uncertain. Whereas previously, when we sampled the point, we knew that was a function value f. Okay, so back to active learning. Just a reminder, we have our unlabeled data set. The agent picks a point from that, learns the label, adds it to its labeled data set, and repeats. Okay, so one of the main approaches to this problem is Bayesian information theoretic active learning. So the goal is just to reduce the number of possible hypotheses as fast as possible. Or in other words, reduce our uncertainty of the latent function as fast as possible. In the probabilistic case, the optimal solution is to pick the points d prime, so the data points d prime that minimize entropy after you've sampled them. But obviously, in general, you can't calculate this in advance. It's not possible because you don't know labels. So instead, you do a greedy approach. So for each point you want to query, you pick the point that will give you the maximum expected decrease in the entropy, decrease in uncertainty, sorry. Okay. Possibility theory, we don't have, the entropy doesn't make sense. So we need a different measure of uncertainty if we're going to take a similar approach. So we've, with my supervisor, created this total uncertainty measure. So it's essentially just the integral of the possibility function. So why that makes sense, let's come back to these two examples. So if you know nothing, you've got your possibility function, which is 1 everywhere. If you integrate that, that's going to be infinite. So if you know nothing, you have infinite uncertainty. And then another case, if you know everything, so you've got perfect information, if you integrate that function, you get 0. So you have no uncertainty. For active learning, we want to consider the uncertainty ratio between our current uncertainty and our future uncertainty once we learn the label at that point. So we consider the ratio of the total uncertainties. Because we're working with normal distributions, that integral is super easy. It's just standard deviation, and once we do the uncertainty ratio, we're just left with the standard deviation before we observe the new label and standard deviation after we learn a new label. So obviously, we don't know what the new label is going to be, so we have uncertainty about the label. So we consider the maximum expected uncertainty ratio. So here, G1, if G1 is our possibility function before we learn the new label, and if G2 is our possibility function after we learn the new label. So we consider the maximum expected uncertainty ratio. So plugging in the standard deviations that we had before, we already know what the uncertainty at the moment is, so that can come out of the max expected value, and then we're left with the maximum expected value of 1 over the new standard deviation. And just putting in the formula for maximum expected value, we have this primum of the possibility of that a latent function value times the expectation of the 1 over the standard deviation given that latent function. So that expectation is the probability that we observe label 1 times the standard deviation we would get if we observe label 1, and then the probability that we observe label -1 times standard deviation we get if we get label -1. Okay, so what does that look like in practice? Here, we don't have a sample point at x equals 3. So if we have our current standard deviation at x equals 3 as the blue area. And then once we sample, if we observe label -1, then we're left with this uncertainty here. So we can calculate the uncertainty ratio. And then if we observe label +1, then we have this uncertainty. So the maximum expected value is going to be, well, the sum of these scaled by how likely they are to occur. Okay, so as for an experiment, here's a very simple one. We've got the linear separator x equals y. We get +1 if we're above, -1 if we're below. But our labels can be incorrect, and they're more likely to be incorrect the closer we are to that linear separator. So I ran this, and the agent could pick 20 different points to learn from, and ran it 100 times. So this is the average performance over 100 runs. So here we've got the latent function error after each of those choices. So this is the average over the 100 runs. Our approach is in green. The orange is just random, so that's just pick a random point at each time. And then bold is one of the best performing existing active learning approaches. So you can see ours performs a little bit better than bold and a lot better than random. And then this is the same experiment, but this is just the proportion of labels that it gets correct after each choice. And again, a little bit better than bold and quite a bit better than random. Okay, and then this is another experiment that comes from the paper that bold was published in. So we've got a checkerboard, so +1 if it's a square, -1 if it's a red dot. And here, there's not any uncertainty about what the correct label is. If you're somewhere that there's black dots, then you're definitely getting +1. If there's red dots, you're definitely getting -1. And unsurprisingly, we perform very similarly on these kind of experiments because there's not that additional level of uncertainty that we can model correctly. Okay. So in summary, possibility theories of practical and empirical modeling both deterministic and random uncertainty. Active learning can be used to minimize the number of labeled examples you need. As we just saw from the experiments, these algorithms based on possibility theory can perform quite strongly on active learning problems compared to standard approaches. Oh, I forgot to mention this. Okay, I'll go back and I'll explain it to you. Yeah, okay, so here, this is depending on sigma G2, so that's our the standard deviation after we learn the labels. But obviously, to find that, we need to train our model, which is quite expensive. So this is a problem. So you've got to do that for every single point that's unqueried and every single potential label. So that can get quite expensive quite quickly. And that's a problem that exists in every information theoretic approach. But there's good approximations for most of the existing ones. We don't have one yet. So that's where what we're working on now is to find an efficient way to calculate this without having to find all the future standard deviations. So that was that point. And that's me done. So thank you for listening.